In this video, we will consider the behavior of a function for large values of x. So let's repeat our common procedure for the function 1 over x as x gets very large positively or negatively. Okay, so let's start with the positive part. So here we will get values like this. So our function looks like this. So notice that in the first table we can conclude that as x gets larger and larger, the value of the function approaches 0. So we denote this as follows. The limit when x goes to infinity of f of x will be equal to 0. And we have the same situation when x decreases without boundary negatively. So in this second case, we say that the limit when x goes to negative infinity of f of x, it's also equal to 0. So this will be our definition for limits at infinity. We will say that the limit when x goes to infinity of f is equal to L if f approaches L as x increases without bound. And the same thing we will say that the limit of f when x goes to negative infinity is equal to L if f approaches L as x decreases without bound. So the key word is, in this case, we're studying when x increases without bound, and the second case is when x decreases without bound. So to compute limits at infinity, we will need some basic examples that will allow us to compute more complicated limits. So the first one is that both the limit when x goes to infinity and when x goes to negative infinity of a constant is the constant itself. The second one is the limit when x goes to infinity of a constant divided by x to the p is equal to 0 when p is greater than 0. So remember, in our case, in the first example, we said that the limit of 1 over x when x goes to infinity was equal to 0. So in this case, we took p as 1. The last case we will need is the limit when x goes to negative infinity of c over x to the n. It's also equal to 0, but now we're restricting to n positive and an integer. So remember that we did the limit when x goes to negative infinity of 1 over x was equal to 0. So in this case, we said n equals 1. So now the trick to find limits at infinity of a more complicated rational function is to first divide each term on the numerator and denominator by the highest power of x that appears in the function. And after doing that, we will use the limit 1, 2, 3 that we just mentioned to compute the final limit. Let's see with an example how to do this. Okay, so let's try to solve these limits. So we have to find the limit when x goes to infinity of x plus 5 divided by 2x minus 2. So remember, to start these kind of problems, we have to divide every term in the rational function by the highest power of x appearing in the function. So in this case, the highest power is just x. So we will divide everything by x. And we'll get the limit when x goes to infinity of x divided by x plus 5 divided by x. Remember, divide every single term. 2x divided by x minus 2 divided by x. And because x is not 0, we can simplify these expressions a bit. So we can simplify this and this to obtain the following. So x goes to infinity of 1 plus 5 over x divided by 2 minus 2 over x. And now we have a sum of limits that we know how to compute. So we know that the limit of the constants will be just constant, and the limit of these two things will be 0. So let's put all of that together, and we will get that this is equal, by using properties of the limit, equals to the limit of 1 plus the limit of 5 over x divided by the limit of 2 minus the limit of 2 over x. Okay? The first one is 1. The second limit here is a constant divided by a positive power of x, so the second one is 0. The third one below here is just 2. And this last one, it's again 0. So the limit of this will be 1/2. Let's try doing the second one, the second example here. So now we have the limit when x goes to negative infinity of this rational function, x squared minus 2 divided 4 minus x. So again, the first step should always be divide your every single term by the highest power that appears in the function. In this case, the higher power is x squared. So we will divide everything by x squared. So this will be the limit when x goes to negative infinity of the following: x squared divided x squared minus 2 divided x squared. Again, remember, divide every single term by x squared minus x divided x squared. And again, as before, we can simplify this a bit. And we will obtain then that the previous limit is equal to the limit when x goes to negative infinity of 1 minus 2 over x squared divided by 4 over x squared minus 1 over x. Okay? So now we can repeat the thing we did in the last step, and we see that the numerator, the limit of the numerator will be equal to 1, but the limit of the denominator will be equal to 0. So in this case, we have a case of 1 divided by 0, which we already studied that in this case the limit does not exist. Finally, the last thing to mention about this limit at infinity is that whenever either the limit at infinity exists and it's equal to L, or the limit at negative infinity exists and it's equal to L, we will say that the line y equals L is a horizontal asymptote for the graph.